Charles-Bonnet syndrome. How the brain creates vision without sight. Charles-Bonnet syndrome is a neurological condition in which people with significant vision loss experience vivid visual hallucinations. Importantly, these hallucinations are not caused by psychiatric illness or cognitive decline. Instead, they occur because the brain continues to generate visual activity even when it is no longer receiving normal input from the eyes. In this presentation, I will explain how reduced visual input from retinal or optic nerve damage leads to spontaneous activity in the visual cortex through 3 levels of biological analysis: neurochemical, neuroanatomical, and neural network systems. Charles-Bonnet syndrome occurs in people who have significant visual impairment caused by conditions such as macular degeneration, glaucoma, or retinal damage. Even though the eyes are no longer providing normal visual information, the brain's visual system is still active. As a result, individuals may experience complex visual hallucinations. These hallucinations can include faces, animals, patterns, or even detailed scenes. A key feature of Charles-Bonnet syndrome is that people are usually aware that the images are not real. Researchers believe these hallucinations occur because the brain attempts to compensate for the loss of visual input by generating its own visual activity. At the neuroanatomical level, Charles-Bonnet syndrome primarily involves the visual cortex, which is located in the occipital lobe at the back of the brain. Under normal conditions, the visual cortex receives signals from the retina through the optic nerve. However, when diseases damage the retina or optic nerve, the visual cortex loses this normal input. This loss of input is called deafferentation. When this happens, the visual cortex can become hyperactive because it is no longer receiving the signals it expects. Research shows that this lack of input leads to increased spontaneous activity in the visual cortex. In other words, neurons in this region begin firing on their own, without external stimuli, producing phantom images. This helps explain why hallucinations in CBS can feel so detailed and real. They are being generated by the same brain areas that normally process actual vision. Looking at the neurochemical level, this hyperactivity in the visual cortex is thought to be caused by an imbalance between excitatory and inhibitory neurotransmitters. Specifically, there is reduced activity of GABA, the brain's primary inhibitory neurotransmitter, and relatively increased activity of glutamate, which excites neurons. GABA normally acts like a brake, preventing excessive neural firing, while glutamate promotes activity. When GABA levels decrease and glutamate signaling dominates, neurons in the visual cortex become hyperexcitable and more likely to fire spontaneously. This chemical imbalance contributes directly to the uncontrolled neural activity that produces hallucinations. At the network level, Charles-Bonnet syndrome reflects how different brain areas work together to interpret sensory information. The brain constantly predicts what we should be seeing based on previous experiences and stored visual memories. When visual input disappears, the brain's predictive systems still attempt to interpret visual information. Without external signals to guide perception, these networks may begin generating images internally. In this way, stored visual memories and predictive processes can combine to produce vivid hallucinations, even though no real visual stimulus is present. One important research method used to study CBS is functional magnetic resonance imaging, or fMRI. fMRI measures brain activity by detecting changes in blood flow, which correspond to active regions of the brain. Studies using fMRI have shown that during hallucinations, individuals with CBS exhibit increased activity in the visual cortex, even though there is no visual input coming from the eyes. This provides strong evidence that the hallucinations are being generated internally by the brain, rather than coming from external stimuli. Additionally, fMRI studies have shown altered connectivity between visual areas and other brain networks, further supporting the idea that CBS involves changes in large-scale brain systems. In conclusion, Charles-Bonnet syndrome demonstrates how the brain adapts to sensory loss through neuroplasticity. When visual input from the eyes is reduced, the brain does not simply become inactive. Instead, changes occur across multiple levels of the nervous system. Neurochemical changes can increase neural excitability, the visual cortex becomes hyperactive due to loss of input, and large-scale brain networks attempt to fill in missing visual information. Together, these biological processes help explain why people with vision loss may experience vivid visual hallucinations, highlighting the brain's remarkable ability to adapt to changes in sensory input.